Question 8, Part B. A particle is moving along the x-axis. Its position at time t is given by x equals t plus sine t. Part 1. At what times during the period t greater than 0 and less than 3 pi is the particle stationary? The displacement equation is x equals t plus sine t. Now, velocity is the rate of change of displacement with respect to time. So to get the velocity equation, we find the derivative of x with respect to t, so dx dt. So differentiating t plus sine t with respect to t, we get the velocity v is equal to 1 plus cos t. So we need to solve for t the equation v equals 0. So when the velocity is equal to 0, the particle is stationary. So 1 plus cos t is equal to 0. Rearranging the equation to isolate cos t, we get cos t is equal to negative 1. And solving this equation with respect to t using inverse cos of negative 1, we get t is equal to pi, 3 pi, 5 pi, and so on. But t has to be a value greater than 0 and less than 3 pi. So t equals 3 pi is not a valid solution. Therefore, the only valid solution is the particle is stationary at time t equals pi. Part 2. At what times during the period t greater than 0 and less than 3 pi is the acceleration equal to 0? The velocity equation is v equals 1 plus cos t, which we found in part 1. Now the acceleration a is the rate of change of velocity with respect to time. In other words, dv dt. So to get an expression for a, we differentiate v with respect to t. So the derivative of 1 plus cos t is negative sine t. So we need to solve for t the equation acceleration a equals 0. In other words, negative sine t is equal to 0. And the solutions are t equals 0, pi, 2 pi, 3 pi, and so on. But like part 1, the value of t has to be greater than 0 and less than 3 pi. So the only valid solutions are t equals pi and t equals 2 pi. Therefore, the acceleration is equal to 0 at times t equals pi and t equals 2 pi. Part 3. Carefully sketch the graph of x equals t plus sine t for t greater than 0 and less than 3 pi. Clearly label any stationary points and any points of inflection. Recall that the position or the displacement x is equal to t plus sine t, the velocity v is equal to dx dt, which is equal to 1 plus cos t, and the acceleration a is equal to dv dt, which is equal to d squared x over dt squared. In other words, it's the second derivative of x with respect to t, and that's equal to negative sine t. Now the possible points of inflection occur where a, or d squared x over dt squared, is equal to 0. So we're going to test the points where a is equal to 0. In other words, where t is equal to pi and t is equal to 2 pi, which we found in part 2. So I'm going to use a table of second derivatives and test for a change of concavity around t equals pi and t equals 2 pi. And the values that I've chosen are t equals 3, t equals 4, and t equals 7 around t equals pi and t equals 2 pi. So when t is equal to 3, the second derivative is equal to negative 0.1. And when t is equal to 4, the second derivative is equal to 0.8. So we have a negative second derivative here, a positive second derivative here. When t equals pi, the second derivative is 0. So we have a change of concavity around t equals pi, so that is a point of inflection. And testing around t equals 2 pi, so when t is equal to 4, the second derivative is 0.8, and when t is equal to 7, the second derivative is negative 0.7. So again, we have a change of sign in the second derivative, which means a change of concavity around t equals 2 pi. So we have a concavity change around t equals pi and t equals 2 pi, hence they are points of inflection. Also, the velocity v, or dx dt, is equal to 0 at time t equals pi, and this corresponds to a stationary point on the graph of x equals t plus sine t. Now we previously saw that at time t equals pi, this corresponds to a point of inflection. So if it's a stationary point and a point of inflection, at t equals pi, this corresponds to a horizontal point of inflection on the graph of x equals t plus sine t. Now we need to find the vertical coordinates, or the values of x, that correspond to the values of t that we just found. And we also need to find the values of x that correspond to the endpoints of the graph. Recall that the interval that we're given is that t is greater than 0 and less than 3 pi. So using the equation x equals t plus sine t, at time t equals pi, x equals pi. At time t equals 2 pi, x is equal to 2 pi. At time t equals 0, x is equal to 0. And at time t equals 3 pi, x is equal to 3 pi. So here is a graph of x equals t plus sine t, as best as possible drawn to scale. So here are the endpoints, 0, 0, which is the origin, and 3 pi, 3 pi. Notice the circle there is not included in the graph, since t has to be less than 3 pi. It's not less than or equal to. Now I've labelled the graph, x equals t plus sine t, with the equation. That's important. And the question also asks us to label the stationary points and inflection points. So there's only one stationary point, which is at pi, pi, but it's also an inflection point. And there's also an inflection point at 2 pi, 2 pi. Now to get some extra points, I've done a table of values, which I haven't shown, just to get the curve a little bit smoother and a little bit more accurate.